Chemistry Standard 12 Solid State Part 4. In this part we will learn about electrical properties of the solid like conductors, insulator and semiconductor. Out of these three, in the previous part we have already completed conductor and insulator. In this part we will learn about semiconductors in detail. Conductors, insulator and semiconductor. First we will learn about, we will just do the example. Conductors, all the metals are a good conductor of electricity like gold and copper, aluminium, etc. Insulator, we can have rubber and we can have wood are a good insulator, and semiconductor like silicon and germanium will work as a semiconductor. Now according to the definition we will just divide it. The solids with a conductivity ranging between 10 to the power 4, it is not 104, 10 to the power 4 to 10 to the power 7 per ohm per meter are called conductors. Metal have a conductivity in order of 10 to the power 7 per ohm per meter are good conductors. Insulator, these are the solid with very low conductivities ranging between 10 to the power minus 20 to 10 to the power minus 10 per ohm per meter. Semiconductor, these are the solids with a conductivity in the intermediate range from 10 to the power minus 6 to 10 to the power 4 per ohm per meter. Conduction of electricity in metals. Metals conduct electricity in solid as well as molten state. The conductivity of metals depend upon the number of valence electrons available per atom. The atomic orbital of the metal forms molecular orbitals which are so close in energy to each other as to form a band. First we will understand this point. Metal, it is having an atomic orbital, and all the atomic orbitals of a metal will combine and they will form molecular orbitals. And these molecular orbitals will combine and they will form energy band, and this one it is known as band. And here they will combine and they will form two type of band. One it is known as valence band and one it is known as conduction band. Valence band has a low energy level and conduction band that is a higher energy level. Highly occupied band that is known as valence band and unoccupied band that is known as conduction band. This in detail we will study about the next slide. If this band is partially filled or it overlaps with a higher energy unoccupied conduction band, then electron can flow easily under an applied electric field and the metal show conductivity. If the gap between filled valence band and the next higher unoccupied band is large, electron cannot jump to it, and such substance has a very small conductivity and it behaves as an insulator. Now we can understand this by a very nice diagram over here, clear diagram about conductor, semiconductor and insulator. You can see the conductor, this downward energy level, low energy level. Here energy one diagram it is there, energy graph, low energy level, highly occupied band that is valence band, means it is filled with electron, and upper one band that is known as conduction band. And the gap you can see in the next one diagram, the gap between this valence band and the conduction band is known as energy gap, or you can say forbidden gap. Here also you can see the forbidden gap, and here in the insulator also you can see the gap between this valence band and conduction band, that is forbidden gap or energy gap. Now we are talking about conductor. In the conductor, valence band and conduction band both are overlapped to each other and there is no band gap, and that's why electron can easily jump or move from valence band to the conduction band at normal temperature, and that's why they are a good conductor, or their conductivity is very high at a normal temperature. But when we will move to the semiconductor, you can can see the lower occupied band, that is a valence band, and conduction band, that is highly unoccupied band, higher energy level unoccupied band. The gap between this valence band and conduction band, it is more than that of conductor, but it is less than that of insulator. And because of this energy gap at a normal temperature, the electron cannot move from valence band to the conduction band, and they will show not conductivity at normal temperature. But as we increase the temperature, electron can easily move from valence band to the conduction band, and they show the conductivity. So we can say at normal temperature they will not show the conductivity. At higher temperature, semiconductor will behave as a good conductor. Now insulator, you can see the valence band and the conduction band. There is a very large difference or large energy gap is there between the valence band and the conduction band, and that's why at a very low temperature and at very high temperature, electron cannot move from lower band or valence band to the conduction band, and that's why they will behave as an insulator. They will not conduct electricity at lower and at a higher temperature. The conductivity of this intrinsic semiconductor is too low to be practical use. Their conductivity is increased by adding an appropriate amount of suitable impurity, and this process is called doping. Now we will understand doping. Doping, actually it is a process of to increase the conductivity of semiconductor by adding small amount of impurity in them. Doping can be done with an impurity which is electron rich or electron deficient as compared to the intrinsic semiconductor, silicon or germanium. Such impurity introduce electronic defect in them. Electron rich impurities, silicon and germanium belongs to a group 14 of a periodic table and have a 4 valence electron each. In their crystal, each atom forms 4 covalent bonds with its neighbor. This we have learned in the 11th standard. Group 14 element, that is carbon, silicon, etc. So this silicon, it is a group 14. Outermost it has a 4 electron, and all the 4 electrons will make a 4 covalent bond with its neighbor atom. When doped with a group 15 element like phosphorus or arsenic, which contain 5 valence electron, they occupy some of the lattice site in silicon or germanium crystal. 4 out of 5 electron are used in the formation of 4 covalent bond with the 4 neighboring silicon atom. But what about 5th? The 5th electron is extra and it becomes delocalized. Delocalized means it is easy to move or it is free to move from one place to another. And this delocalized electron increases the conductivity of doped silicon or germanium. Here the increase in conductivity is due to the negatively charged electron, and silicon doped with electron rich impurity is called N-type of semiconductor. Again, this whole thing we will understand by the diagram which will come afterward. Electron deficient impurities, silicon or germanium can also be doped with a group 13 element. Group 13, as we are knowing, boron, aluminium or gallium, which will be only 3 valence electron. So the place where the 4th valence electron is missing is called electron hole or electron vacancy. An electron from a neighboring atom can come and fill the electron hole, but in doing so, it would leave an electron hole at its original position. If it happens, it would appear as if the electron hole has moved in the direction opposite to that of the electron that filled it. Under the influence of electrical field, electrons would move towards the positively charged plate through electronic holes, but it would appear as if electron holes are positively charged and are moving towards the negatively charged plate. This type of semiconductor are called P-type of semiconductor. This thing we can understand by the one next diagram. Here all the things are going to be clear. You can have a 3 First one, that is a perfect crystal. Second one, that is an N type of semiconductor. And third one, that is a P type of semiconductor. You can have in the perfect crystal, all the silicon atoms are arranged, and each silicon atom has a 4 valence electron. This is your 1 electron, second, third and fourth. With the same way, the another silicon, the neighboring silicon atom is also 4. So all that 4 electrons are busy in forming a 4 covalent bond with a neighboring atom. But when you are doping the arsenic in the silicon, so one silicon atom, it is replaced by arsenic. Arsenic, it belongs to the group 15. Group 15 means what? Outermost they are having a 5 electron. 5 electron, out of that 4 electrons are busy in forming a 4 covalent bond with a neighboring atom. But the 5th electron, which you can see here, this 5th electron is free, and this 5th electron is known as delocalized electron. Means it is free to move, and that's why here it is written mobile electron. So this electron can move easily. And suppose if you are keeping here an electric plate, if I keep here the positive electric plate, so this electron will move towards this side, towards the positive electric side, and that's why we can say the conductivity is due to the delocalized or a mobile electron or negatively charged electron, and that's why the name it is given N type of semiconductor. N, that is for a negatively charged electron. Same you can see here also P type. In the perfect crystal, if it is doped with a group 13 element, that is boron, aluminium, gallium. If I doped it with a boron, so boron, it belongs to the 13th group. It has a outermost 3 electron. Out of that, the 3 electrons are busy in the 3 covalent bond. But the 4th one place you can see here. Here actually if it is the 15, then 1 electron will be extra. If there is an atom with a 14 group, 1 electron will be here. But here it is a 13 group element, so 1 electron is missing. And this the place from where the 1 electron is missing, that it is called positive hole, or you can say vacancy or electron vacancy. And this positive hole, now if you will keep the electrode over there, if I am keeping a negative electrode over here, so this positive hole will move towards the negative plate. And as this positive hole will move towards this side, to take its place, the neighboring electron will come here, and this is like the chain. The positive part will move if in the right direction or a left direction, then the electron will move totally opposite to that. And here the conductivity is due to the positive hole, and that's why it is known as P type of semiconductor.
So first of all, a quick recap. Simple semiconductors are made just of the element silicon, but in this video we're going to look at what happens if you dope it. Now doping is adding a little bit of another element. First of all, we're going to add a little bit of a group 15 element. So let's pull out a silicon atom from the lattice and replace it with a group 15 one. Again, this is called doping. Notice there's that extra electron there. There are 4 electrons shared with 4 surrounding silicon atoms and 1 extra one. And when you apply a potential difference, that is a voltage across it, a plus and a minus, that lone electron will be attracted towards the positive electrode by electrostatic attraction. And that is called an N-type semiconductor. The N refers to negative. That extra electron is, of course, negative. Now for P-type semiconductors, you replace or dope a few of the silicon atoms with group 13 atoms. So let's take a silicon again out of the lattice and replace it with indium, which is group 13. Now indium only has 3 valence electrons, so there is now a gap. There is now a missing electron with that right-hand silicon, and that is referred to as a hole. This lack of an electron to bond to that neighboring silicon is called a hole. Now what happens to that hole is an electron can jump into that hole when a potential difference, a plus and a minus, is applied. And as the electron jumps into the hole effectively moves. Now this does seem quite strange. This hole again is a lack of an electron. and so electrons can jump into that space. So why is it called p-type? Well, the lack of an electron you can think of is of something positive. The lack of a negative is a positive, and that's where that p comes from. This hole is moving, as well as the electrons. And in summary, the IB wants you to know what are the charge carriers in the N and P type semiconductors. Well, in the N type, the charge carriers are electrons, and in the P type, it's these holes, which is a lack or an absence of an electron.
Application of N-type and P-type semiconductors. Diode is a combination of N-type and P-type semiconductor, and it is used as rectifier. Transistors are made by sandwiching a layer of one type of semiconductor between two layers of the other type of semiconductor. NPN and PNP types of transistor are used to detect or amplify the radio or audio signals. The solar cell is an efficient photodiode used for conversion of light energy into electrical energy. Rectifier, actually it is a device which will convert the AC current into DC current. Germanium and silicon are group 14 element and therefore have a characteristic valency of 4 and form 4 bonds as in a diamond. A large variety of solid-state material have been prepared by combination of group 13 and 15 or 12 and 16 to simulate average valency of 4 as in germanium or silicon. Transition oxides including vanadium also have a high electrical properties. So in this one part we have completed our electrical properties of the solid. Now in the next one part we will complete the magnetic part, the properties of the solid.